Oh, and the other thing is that we're going to go for around an hour and a half, then we're going to stop, and then have a little break, and then keep going.
Hello, hello. Is that, does it, the sound, I mean, to me the sound sounds the same.
It sounds the same to me.
Is it amplified in some way?
Yes.
Yes?
Okay, a little
Okay,
bit.
good.
Oh, yeah, it is a bit.
Now, the homework thing, that's when Aska said I should, that there would be an examination. So, you know, if people want to take an examination, if you want to take an examination, then you might want to practice before the examination. So it was for that reason that I give the homework problems that. I wasn't thinking that until you mentioned an examination. Okay, so I begin. This is hydrodynamics from the dynamical systems point of view. And the question is, what is a dynamical system? Dynamical system, branch of mathematics, this and that. But what it is, it's an evolution equation. So the simplest way for x dot equals f of x. So maybe I'm not being imaginative enough, but I would say that practically everything is x dot equals f of x. When you say, right, so essentially dynamical systems is not a thing, it's not an object of study, it's methods of studying this ubiquitous thing. I mean, what physical law is not x dot equals f of x, right? That's the Navier-Stokes equations as we said, but it's also, you know, gravity and magnetism and solid mechanics and everything. Okay, so here, but still, to concentrate mind, here are some examples from simple to less simple. In one dimension, you could write x dot equals mu minus x squared. That's pretty much the simplest dynamical system you can write. And that happens to be the normal form of the saddle node bifurcation. And we'll talk about that in a moment. And I wrote n equals 1, meaning that this object of x dot equals f of x, since we're in a math department, x can be a general vector in Rn. So this is n equal 1. Next simplest, something greater than 1, but still very finite, 3. This is the famous Lorenz model, and this is an evolution equation for 3 variables, x, y, and z, and you see the right-hand side given there. Lorenz model, how many people have heard of Lorenz? Edward Lorenz? Okay, so it has, this knowledge has not entirely died out. You've heard of the butterfly effect. It's often Hollywood-esque, a butterfly flaps his wing, and you know, big consequences all over the world, right? That's Lorenz's thing. Was the discovery of chaos and so on. So that's and what he did that with this thing called the Lorenz model, which is right there, which will be the subject of tomorrow's class. Then we get a little bigger. You know the standard joke about mathematicians, how they count. You know, 1, 2, 3, infinity. Right, so that's about what we're doing. 1, we skip the 2. 1, 3, and here's infinity. Navier-Stokes equations. I've written the Navier-Stokes equations. How many people know Navier-Stokes equations? I'm still trying to get to know you. Yes, okay. So, of course, we're used to saying things like, you know, 2-dimensional Navier-Stokes, 3-dimensional Navier-Stokes. So here what I'm talking about is the number of unknowns, the number of things that whose evolution you're studying. This may be two-dimensional, what you call two-dimensional, three-dimensional, but that's not what my point of view at present. This is, the idea is that you have a velocity field u, which it has values u, v, and w, say, or u and v. Anyway, it has values all over the place in space. And for some grid, because I do computations, in x, y, and maybe z. So that you'll have, supposing it was 100 by 100 by 100 grid, then you would have, somebody help me out here, 10 to the 6th points, and you would have 2 variables, u and v, so that would be 20,000. So that would be n there. Or you could be in 3 dimensions, and you could have 1,000 by 1,000 by 1,000. You know, it could go to a million, several millions. So that's the sense in which this is many, many dimensional. And of course, if you're really doing Navier-Stokes, it's infinite dimensional. In computations, it's going to be finite dimensional because, of course, you can only resolve. You only have a finite number of things that you can represent. But in mathematical terms, it's going to be infinite dimensional. Okay, so. As we said, Navier-Stokes will be infinite dimensional. 3D numerical discretization could be something on the order of 1 million, which might as well be infinite. Now, put there, that's perhaps heretical in a math department, but that's the perspective I take. Now you might think perhaps that, okay, many things are described as x dot equals f of x, but not everything. After all, the f could depend also on time, in which case you have x dot equals f of x and t. But you can make, that's called a non-autonomous system, but you can make it into an autonomous system by defining another variable, which here is given the name theta, and you say that theta dot is 1. Meaning it goes through time. So theta is the time, and it's changing in some trivial way. And now you have a new system with one more dimension than the original one, and it's become an autonomous dynamical system. And you might say, okay, but still, there's something more. There you could have a second order differential equation. Why do I only have x dot? What happened to x double dot? What happened? Okay, and there the answer is you can make a new variable which you call x dot, and then you have x and x dot that vary in that way. That is to say, you call y x dot, and so y dot, that's x double dot, is going to be f of x and y. So everything is actually a dynamical system, even things that you might have thought could be exceptions. Okay, so as I said, dynamical systems cover everything. So how can we say we're going to study dynamic systems? Are we going to study everything? Oh, it's a point of view. And you start off with objects that are simple, and we're going to build up to more complicated ones. And the simplest things are fixed points. So we start off with x dot equals f of x. We're going to look for fixed points. Fixed point, it doesn't evolve. It's fixed. That is to say, f of x is 0. So x dot is 0. It's not going anywhere. Okay, so let us draw some f of x. And it's crossing 0. It's going to have the 0 value right over there, because we said we're interested in fixed points. And, okay, and here, let's see, I can do it, yes. And here it's crossing 0, and here it's crossing 0. Okay, but we said that x dot is f of x, and here f, in this thing, f is negative for these x's. Right? If f is negative, then x tends to decrease, and that's what this arrow means. X is decreasing. Here, f is positive, so x tends to increase. So that's what this arrow means. That means that this point is actually unstable, meaning if you're to the right of, or to the left of that special point where f of x is 0, you are going to leave. In contrast, if you have a negative slope, then over here, for these values of x, f is positive, so that you have an arrow going this way. Here, f is negative, so you have an arrow going leftwards, and hence you move in. So we can do this formally with math, Taylor series, standard thing. Let us have a fixed point x bar, and let us see. The x bar is not going to change in time, it's the fixed point, but let's look at a perturbation of it and how it evolves. So we write x bar plus epsilon of t, and that, of course, evolves like f of x bar plus epsilon. That's what the dynamical system is doing. And so that gives us epsilon dot, since x bar doesn't evolve. And now we're going to do a Taylor series expansion here. So we'll have f of x bar plus f prime of x bar times epsilon plus 1/2 f double prime of x bar times epsilon squared, and so on. And what do? Well, f of x bar is 0 by construction. Epsilon being small, you can imagine, epsilon being called epsilon, it's going to be small. That's what epsilons are for. So this term is going to be neglected, and so you end up with epsilon dot equals f prime of x bar epsilon, a very simple linear differential equation, the simplest differential equation there is, pretty much, whose solution is an exponential. It's e to the t times this scalar, f prime of x bar, times the initial value. And so this tells us what we just saw graphically. That is to say that this perturbation, epsilon at time 0, is going to grow if f prime is positive, and is going to decrease if f prime is negative. Okay? So that's the basics. The simplest thing you can do with a dynamical system. Now, that's not very interesting, and I said that we were going to look here. Well, no, it's interesting, but it's finished. Now we know everything about it. Now we're going to go to a system that might have more than one solution. because of the x squared. And so we're going to look at this normal form of the saddle node bifurcation. We're going to look at x dot equals mu minus x squared. So here we are. We've plotted mu minus x squared for 3 different values of mu, negative, 0, and positive. And again, we're looking for roots. We want to see when it crosses 0. And here it doesn't cross 0 at all. Right? It's a quadratic that doesn't have a solution. Here it has a single double root, and here it has 2 roots. And by this principle that we saw before, this one has a positive root. Actually, this root has a positive slope, and hence this fixed point is unstable. Perturbations are going to grow like e to the t f prime, which is positive of x bar. It's unstable. And this root has a negative slope, and hence it's stable. Okay, and all this works out topologically. That is to say, if you wonder where you're going to go when you're on the x-axis, if you're to the left of this hollow point, you're going to go to the left. If you're to the right of this dark point, you're going to go to the left also, because the f is negative. Recall that the sign of f gives you the direction of motion along the x-axis. And if you're in between, you're going to go to the right. F is positive. So everything works out. You know where you're going, depending on where you are on the x-axis. And again, you can turn the crank and do these calculations. It's all just doing in symbols what we did graphically. This is the normal form, mu minus x squared. The fixed points are their solution, the roots of this f, meaning x equals plus or minus square root of mu. These exist only for mu greater than 0. That is to say, here there are no fixed points, as we saw. And their stability is governed by f prime of these 2 fixed points, and that the derivative of this is minus 2x. And one of them is negative and one of them is positive. So we get minus plus 2 square root of mu. So one of them is stable and one of them is unstable, just as we saw graphically over there. The calculations tell us the same thing. And this, okay, we have the normal form, yes, but what about other possibilities? Mu minus x squared might look a little bit special, but in fact it covers all quadratic functions. Supposing you had a general quadratic polynomial, let us rewrite it in this way. We're going to gather together the, we're going to move x, and we'll move mu, effectively, so that we write it as plus or minus mu, and some new mu, plus or minus x squared, some new x. That's a general quadratic polynomial. You can see above I wrote linear, constant term, a linear in x, a linear in mu, and x squared. And for this, there are 4 cases, which are going to depend on the signs of the coefficients. And now we're going to switch convention, and we're going to put in a convention that we're going to use throughout. That is to say, over here, we had f of x, and we had to have 3 different diagrams according to whether the sign of mu. But now, we're not going to show f anymore, not explicitly. We're going to have x on the vertical axis, and we're going to have mu on the horizontal axis. So this situation here is going to be shown in a single diagram over here. That is to say, we have mu varying, and this is the roots x bar. Okay? And you recall that for mu negative, there were no roots, right? Because the parabola was below the axis. And then there was a double root, and then there were 2. And the higher one was stable, and the lower one was unstable. So now the arrows go in the vertical direction, because this is the direction of the x. Okay? Again, this is going to tell you everything you need. If you are in this region, these arrows tell you, oh, I see, I go upwards until I stop here. If I live here, if my initial condition is here, I learn, oh, I'm going to go downwards until I stop here. You've seen already the convention of using hollow dots to represent unstable states, and you see now the convention of using dashed lines or dashed curves to represent branches of unstable states. These are branches, meaning each one of these would have been a dot, a solid dot in the previous slide, and each of this would have been a hollow one. Now, according to the signs of in front of the mu and the x squared, you have 4 different cases, which are shown here. If excuse me, if you change the overall sign of everything, that's the F, and remember the F tells you the direction of the arrows. And so we see here that we've switched the arrows. There was a down arrow, and now there's an up arrow, and there was an up arrow, and now there's a down arrow. So that's what happens when you switch the overall sign of mu minus x squared becomes minus mu plus x squared. There are also 2 other possibilities of sign. We could switch this sign of just mu, and that tells us that everything that happens from mu positive instead happens from mu negative. So that's taking this picture and flipping it there. And so that's here, where we just put that, the new mu is the negative of the old one. And then, of course, we could do the same thing with this. We flip this mu. So those are the 4 possibilities. But you see that they're all essentially the same. And that is to say, for some mu values, you have no solution. And for other mu values, you have 2 solutions, one unstable, one stable. So there is only one saddle node bifurcation. You know, who cares whether you're calling it positive mu or negative mu? Who cares whether you're calling it plus x or minus x? There is one saddle node bifurcation, and here it is. Now, why would I emphasize that? Because the next bifurcation, called a pitchfork bifurcation, there will not be just one of them. There are 2 of them. Okay, but let's start looking at them. Let's look at a normal form. Oh, first I should ask, are there questions? Let's see. Okay, I want it. X dot equals mu x minus x cubed. Okay? There's, I've gone back to the original easy convention. I've drawn f of x for 3 different mu values, mu negative, mu 0, mu positive, and that's the function mu x minus x cubed. You know what minus x cubed looks like. It looks like this. For mu positive, you can counteract the negativity, the minus x cubed, and have it go the opposite sign for a while. Okay, and you can see again by the graphical conventions we saw before. This having negative slope, it shows this is a stable fixed point, and this is borne out by the fact that f is positive here. So you go towards increasing x. It's negative here. You go towards etc. etc. Here, for mu positive, you end up with 3 fixed points, not 2, not 1, but 3. The inner one has become unstable, and the outer one has become stable. So this does bear a resemblance to the saddle node bifurcation in that you increase the number of fixed points by 2. Before you went from 0 to 2, now you're going from 1 to 3. You cannot...
Explain saddle and node.
Oh, let's see. The saddle node bifurcation was the previous... Okay. Right. Yeah, okay. This thing here is called a saddle, and this thing here is called a node, but I can't say yet why I use that term. That will be in about 20 minutes. I'll say why they're called saddle and node. Okay, but thank you. So saddle node bifurcation is a collision between a saddle and a node. They're colliding here and then going away. And we'll talk about why we should use, why isn't it called a stable, unstable bifurcation, right? I said that one's a stable, one's an unstable, but we'll talk about that in a second. And so pitchfork bifurcation, and you'll see why it's called pitchfork that in about 1 minute. So you're going, before you're going from 0 to 2, and now you're going from 1 to 3. In both cases, you're making two more fixed points. Why 2 more? Why can't we go from 1 to 2 or from 0 to 1? You can't by topology. All your arrows would have to switch at once. You can see if you had this, and now all of a sudden there was a place where you were going to the right, well then you would have to switch the arrows every place at once. Whereas here you can do this continuously. You have a little teeny infinitesimal section where you're going to in the opposite direction as before. And overall, if you sit in the back of the room and you don't wear your glasses, the situation here actually looks like the situation there because all this kind of merges into one. You can do this continuously. You can go from here to here continuously. You haven't changed the directions of the arrows over at infinity. You can't make it instantly changing all the directions every place at infinity. You've got to do it little by little. It's continuous. Everybody understand what I'm saying here? If you agree if you weren't putting on your glasses and if you were far back in the room, you might mistake this situation for this one. It's only different locally. And for mu sufficiently small, you can barely see it. Imagine in this picture, I could tell you, although it's not true, that there's a tiny region where it's negative here and a tiny region where it's positive here, and that's just too small for you to see. Right? So it happens, and that is true for very, very, very small mu. So this happens continuously, and it has to, and for that, topologically, you need to have two fixed points created. You might say, you left out a bunch of points here. Before I had a constant, a bunch of terms. There had a constant and an x squared, and now I have an x and an x cubed. What happened to the constant? What happened to the x squared? Well, the answer is that this happens when the physical problem that you're modeling is such that there's symmetry, and that leads to f having to be an odd function in x, and this is a truncation of an odd function in x. And now again, as before, we can do all the calculations, let's see, and I think I've done them in the next slide. Yes, all the calculations are done here with the stability and unstability. Let's not do that. Let's draw the graphs. Let's go back to this. You recall we went from 1 to 3 points, and the inner one that was stable became unstable and was surrounded by 2 stable points as mu increased. So that's what's drawn here. You have a stable point, and here you have an unstable point surrounded by 2 stable points. Right? And that's as mu increases. This is mu equals 0, 1 solution which is stable, 3, 1 unstable surrounded by 2 unstable. And we can play the same game as before where we switch the signs in front of the mu x, we switch the signs in front of the minus x cubed. And as we did before, if you switch the signs of everybody all at once, from let's say this one and this one, you get this, which merely tells you to reverse the arrows. So all the arrows here become reversed. Anything that used to be stable becomes unstable. Everything that was dashed becomes solid becomes dashed. Everything that was dashed becomes solid. And you can see that's what's happening here. And you see that this situation is fundamentally different from this one. You started off here with here you had 1 stable point, and you had here an unstable point, 1 stable point here, and 1 unstable point surrounded by 2 stable points, whereas here you have 1 unstable point and you end up with 1 stable point surrounded by 2 unstable points. So that's this situation is fundamentally different from this. There's no redefinition of mu or x that would change that. This is different. And this one's called supercritical, this one's called subcritical. And then there are 2 more variants that just involve what you call mu. Whether you call mu, this is just a flip. This one flips that one just by changing the definition of mu, and this one flips that one by changing the definition. Okay, so here there are 2 kinds of pitchfork bifurcations, and this is the math. This is where you solve for the fixed points, where you solve for the stability, and I won't go through that. Here are some more variants of pitchfork bifurcations. This one is called imperfect. Remember I said that why would you have a mu x minus x cubed? What happened to the constant term? What happened to the quadratic term? And I said, well, because there was symmetry, and hence that imposed that f had to be an odd function. Okay. Supposing it's mostly like that, but it's not perfect symmetry. What you get is this situation where it looks, again, if you go back, and don't put on your glasses, this looks from far like a pitchfork bifurcation, but you see it's not exactly. There's a finite difference here, and there's a difference between this branch and this branch. This is called an imperfect pitchfork bifurcation. And in fact, if you are an experimentalist, probably this is the only kind you could ever see because you never have perfect symmetry. And in fact, even if you're a numericist, you don't, because you're going through your do loops from 1 to n and not from n to 1. You pretty much never have perfect symmetry unless you impose it. So in fact, what you really see is this, except if you're a good numericist or a good experimentalist, this distance is too small for you to see. Okay. And what is this a graph of? This is a graph of the fixed points of mu x minus x cubed with a constant term here. Then another thing is this subcritical bifurcation. You recall that we said that here we have these unstable fixed points. So what does this imply? If you're over here or here, you're leaving, you're going to infinity. Physicists in particular do not like that idea. What do you mean you're going to infinity? What's over there in infinity? It's kind of very far away, and that doesn't sound very reasonable. So generally, physicists or other applied scientists do not accept this situation. And so what they call a subcritical bifurcation is something that looks like this. That is to say, take your mind off these dark places here, and it looks like a subcritical bifurcation. You have the unstable one here. You have here a stable one surrounded by two unstable ones. You leave here, you leave here, you leave here, you leave here. But put back those dark ones, and you see that you leave, but you don't go to infinity. You're caught by this. You leave here, but you don't go to infinity. You're caught by this. And what do you mean you're caught by this? Well, what's this a picture of? This is a picture of the subcritical pitchfork bifurcation normal form with another term added on, which is of higher order, x to the fifth, and it has the correct sign. You may not remember this, but let's go back to this picture. What was the difference here? If you put in a plus x cubed here, that's how you went off to infinity here. Okay, so you can put in a plus x cubed, but now if you're going to put in a minus x fifth, that will have the correct sign to bring you back from infinity. So again, close by, if you just drew a little zoom here of this, it would be the subcritical bifurcation. But if you then looked at the whole picture, you wouldn't go to infinity, and so you would feel it was physically possible. Yes?